photograph of the banks of the Tiber on one of my many trips to the home country in Rome. My name is Phil Farina. I'm speaking to you today from the Clear Creek offices in Northwest Ohio. I'm the Midwest Business Development Manager for Clear Creek, and I've got about 35 years of experience in the water treatment technology design arena. So there's a lot to cover today, and I want to make sure that we have the opportunity to present everything that would be an advantage for what you're going to be looking at in PFAS management. So for an agenda, I'm going to do a brief introduction. I'm going to delve directly into what do we need to know before deciding on a solution. And I'm going to spend a lot of time in that area because one of the things that I think we see a lot of is people are making technology decisions perhaps too early in the planning stages. And I want to help you understand why that planning stage is extremely important and can be utilized not only to give you the best system, but also help you in the economics of that system. We're going to go through that, and then we're going to talk about the current state of technologies, things that are available for immediate application in the field, and how that comes together in a holistic approach and bringing systems together in a systems integration. Then we'll have a little bit of a conclusion discussion, and then I'll open it up to questions. So a little bit of an introduction. Clear Creek Systems and our sister company, Yukon Technology, have developed a strategic technology partnership designed really to work with the field organizations, the environmental engineering companies, the stakeholders, the federal market space, the state and municipal market space, where the people need to have a technology to bring together a methodology of reducing their PFAS contamination. We are known as a water treatment leader in applying new technologies to the market since 1974. We have the capability of bringing in a plethora of technologies. We're technology agnostic. We don't sell resin, we don't sell carbon, we don't sell clay, but we utilize all of these medias in order to bring together the best solution for the problem at hand. One of the important aspects of the Yukon Technology, our sister company, is that it does fill a diversity requirement for any of those organizations that have a diversity requirement, specifically in the areas of state and federal jurisdiction. And in some cases, for industrial set-asides, we do meet that requirement. What is our goal? What is our mantra? Our goal is to provide an engineering solution to the most difficult of water treatment problems. We do not give you a round peg, square hole solution. We work with you to develop the specific needs for that specific project. So let's delve in a little bit about that first section of our discussion. What do I need to know before I start? I believe this is critical, and I've been working this concept of understanding my problem before I develop the solution has been an advantage over many, many projects. So when we're looking at PFAS as a problem in water, let's look at that water first. Is it groundwater? Is it well water? Is it pond water? Is it a bloom? Is it industrial application, municipal application, landfill, stormwater? All of these are different, and these different waters may require different treatments. So by understanding, at least initially, what the source of water is, it helps us as a technology supplier to develop the right solution. What's the water going to be used for? Is it drinking water? Is it going to an NPDES outfall? Is it going to the river? Is it a wastewater treatment system? Is it a primary water treatment system? Can you use it for irrigation? This assists us in determining what the treatment requirements are going to be so that we can understand the full dynamics of that system. What created this waste? Is it a waste stream that is an industrial waste stream where we may be looking at other contaminants that are involved? Or is it an aquifer that is being used for drinking water, which allows us to look at the water from a completely different standpoint? So these 3 bullet points are very critical before we go down the path of developing a treatment solution. One of the things that's critical, and once we've defined the water, is looking at the characteristics of the water itself through analysis. It is costly to some extent to do the necessary analysis, but I guarantee you it will save money in the long run when it comes to systems design. At a very minimum, you should look at TSS, TDS, what's the pH of that system. Critical to treatment is the speciation of the PFAS molecules themselves, and we'll go through that throughout the presentation. But speciation can help you define the media that is going to be used to remove them. Are there metals in the water? Some metals have a competing space for the media. So if we have a lot of metals in the water, we may have to choose some treatment in front of the media removal, or we may have to use a completely different technology. Organics, VOC, all of the things that are in that water need to be known in advance so that we can look at the right system. An important aspect is how's the water being delivered to the system? Is it a direct flow? Is it going to be through a series of retaining tanks? What is that flow? There's a difference between a 7-gallon-a-minute system and a 7,000-gallon-a-minute system. All of these criteria known in advance help to define that system design. Once we know that part, let's start drilling down to what is our treatment requirements. Now, this is something that's changing almost on a weekly basis. In the state of Michigan and in the state of California, there are now new rules and regulations that are being applied to PFAS limits. And in some cases, the 70 PPT limit has been dropped down to as low as 7 PPT. It's important for us to understand what is the limit that we're trying to reach. And is the limit a current limit, or is it something that could potentially change in the future? If there's a permitted limit, it is important to understand the criteria behind that limit. While we're looking at the treatment of PFAS, we also need to look at, are there other limits involved in that treatment? In some cases, if you're going to an outfall, TSS, pH, metals, VOC, all of the other contaminants that might be in that water also need to be considered before it can go to the permitted outfall. Once we have this background, then we can start delving into, are we looking at a permanent system or a temporary system? There are many things you can do in a temporary system that you would not do in a permanent system. There's also many things you would do in a permanent system that you would not do in a temporary system. So understanding if it's a long-term or a short-term project helps us to design that system correctly. A critical aspect is flow rate. One of the reasons why we look at flow rate is for sizing of the equipment. And when you're dealing with media, one of the things that's important is the evaluation of the empty bed contact time. The faster the flow, the larger the vessels may need to be, because you have to maintain a certain amount of contact time within the media vessels. And I'll go into that in detail as we go further. And in some cases, we want to look at, particularly in the area of resins, whether we want to use a regeneratable resin or use a single one-time through and replacement resin. So we'll delve a little bit into that when we get to the resin discussion. So this is what we need to know before we start. With this information, let's begin to look at the medias that are currently available that have proven use in the PFAS remediation market. Everyone knows about carbon. Newly onto the marketplace is the organoclays, and even more recent, we have the ion exchange resin systems. So looking at carbon, it is a very well known, has a very long and significant history. It's used very generally in many, many applications as the primary or go-to media. There are two forms of the carbon, either a virgin or a reactivated carbon, and they have a different value in the chain. In some cases, you will find that virgin carbon may cost a few dollars more, but because it's a short-term project, you will get a better bang for your buck by using a virgin material. The reason why we needed to know the PFAS speciation is because, as you're familiar, PFAS comes in long chain, short chain, mid-range, and also comes in very branched chains. And there's different types of hydrophilic ends, hydrophobic ends. There's different type of pH ranges and pH preferences. By knowing these things and determining that if we have a mid-range and a longer chain range molecule, that lends itself well to carbon. If we had only short chain or only branch chain, we may want to choose a different media. So it's important to understand what those speciation is. Carbon comes in two general forms: a renewable carbon source, which is essentially coconut fiber or plant fiber based material, or the mined carbon source, which is the bituminous coming from coal. Each of these materials have a different affinity for different forms of PFAS, and we'll drill into that a little bit later. Organoclays, a little bit new on the marketplace, but very well respected. These are frequently used in conjunction with other medias. And not only can they be used as separate vessels, but they can be blended with maybe carbon or other materials to improve the overall performance of that organoclay. The nice part about organoclays is they also function to remove other contaminants such as oils, heavy metals. If you have PCBs in your water, if you're treating a landfill leachate and you have PCBs in the water, you might find that the PCBs as an oil will coat the carbon. So if you're using a carbon alone system, you'll exhaust that carbon very, very quickly. By adding a organoclay to that system, you will be able to remove the oil from that system through the organoclay and allow the carbon system to work better. So again, knowing what's in that water, what the constituents and contaminants are, we can determine, are we using just clay, just carbon, a combination of each. The ion exchange resins, newer technology, very well respected. Many different forms of ion exchange resins are available. They're frequently used in conjunction with carbon, but in some cases, again, depending on the conditions, you may use alone. Particularly if it's a short-term project, you might not need to have a very extensive treatment system. One important aspect about ion exchange resins is they are man-made polymers. So they can be made to be PFAS specific. And you can break that down further into PFAS, PFOS, PFOA, PFX, all of the different types of fluorinated chemistry. There are some tweaks and ginks that you can do with the polymers to make them more specific to that material that you're trying to remove. So PFAS is also a man-made material or a man-made chemical. Therefore, you can have a designer-made material to take out a designer-made contaminant. Ion exchange resins really like the long and the short chain systems. So again, knowing what you have will help you determine what your media will look like. One of the great things about ion exchange, you can get to those very low target levels. In a lot of cases, we talk about target levels in the non-detect range. But it should be noted that non-detect does not really mean there's no PFAS in that water. The current detection limits is around 2 ppt. So there may still be small amounts of PFAS in that treated water. It's just below the current detectable limits. Let's drill a little deeper. Carbon, we talked about two different sources. You have the virgin source and you have the regenerated source. Some of the positives about carbon systems is they're relatively low cost. Carbon is very easily obtained. However, it should be noted that under the new COVID rules, we're starting to see carbon sources are becoming less and less plentiful as some of the fiber source carbon from India is now, we're seeing a reduction in the production by as much as 20 to 40%, and then recent increases in the tariffs are putting some pressure on that low cost column for the carbon. So we're seeing some changes in that ease of availability. Carbon comes in a variety of packages. You can have it in super sacks and bags in bulk, which makes it very easy to put it into a system of any design. Disposal of carbon, much like most of the media, can be done directly through incineration. You can do regeneration of the carbon. And there's also, in some cases, depending on the client's requirements, there are landfill options for exhausted carbon. My personal preference is incineration at a certified PFAS incineration complex, only because if done properly, you can eliminate the potential return of PFAS by its thermal destruction. Carbon itself is really great for short-term projects because of the speed at which the carbon works and the fact that it will take up a significant amount of the PFAS, but you do have an exhaustion curve, and we'll talk a little bit about that exhaustion curve next. The other piece about carbon that's really great is it has a high flow capability. It doesn't pack very hard. So you can move a lot of water through a carbon vessel, which is very helpful if you have a high flow type of a system. Some of the negatives that exist with carbon is if you look at the exhaustion curve, it does exhaust relatively quickly. And if you're looking at a lead lag scenario, which is always recommended with any of the media, you may get a frequency of change out in the lead vessel because carbon will pull material out very quickly. And then 3 weeks, 6 weeks, 9 weeks later, you'll start to see that level of PFAS passing through the lead vessel starts to go up a little bit. At some point in time, it will go above the desired limit. And even though it's still taking out some of the PFAS between the input bound and your set limit, you're going to change out your carbon at that point in time. So keep that in mind for a minute when we start talking about treatment trains where we're adding carbon to a resin or adding clay to a carbon system. We can allow that carbon to do a much stronger job by keeping that exhaustion curve extended just a little bit. With carbon, and carbon alone, it's going to be very difficult in some applications to get down to that 7 ppt. It's really good at 70. It's excellent at 20. Depending on what else is in that water, it's a little bit difficult to get down to 7 ppt. If you have a lot of TSS in your waste stream, carbon can get easily clogged because it is an excellent media as a filtration media. So we have to take a look at making sure that we have pre-treatment in front of those carbon vessels. And in all of the medias that you look at, some level of filtration is really required in order to protect that media. So when we're designing a system, we're always going to look at that TSS level, and we're always going to try to look at some level of filtration, whether it be sand filters, bag filters, cartridge filters, something to get that TSS level down. An unfortunate negative for a carbon system is some PFAS molecules will pass right through the system. And there's also the possibility that there is a preference for certain types of speciation where it'll grab that species initially and it will hold on to that bond, and then a more desirable species will come by. It'll let go the first one, capture the second one, and that first species may pass through the rest of the carbon and be found in the treated water. So it's not an absolute permanent connection. There is some level of potential replacement. We talk a little bit about virgin and regenerated carbon. Regenerated carbon is a way to reduce your cost of carbon in the system, but it's typically about 80% effective in most cases. So again, if you're using a short-term project, you don't have a high amount of contamination in there, we might look at using a regenerated carbon as a cost-effective way of treating that PFAS. So looking at it on a global basis, there is a high potential total cost of use when you're dealing with all of the parts and pieces of a carbon alone system. What does that carbon system look like typically? Well, let's go a little bit deeper and talk about the sources of carbon, whether it's coconut shell, which is the fibrous material, bituminous, which is the material from coal. These have different capacities for different PFASs. So before we choose the carbon, we need to know that speciation. Vessels tend to be pretty good sized because you need at least 10 minutes of empty bed contact time. So if you have a high flow, you're dealing with a fairly good size treatment system. Carbon should always be set up in a lead lag configuration. This allows that lead vessel to do the bulk of the work, and as it begins to reach that exhaustion curve, it's still pulling out some PFAS, but reducing the pressure on that lag vessel. So you don't really want to have a single vessel system. If you do, you'll end up pulling out the carbon much more prematurely. A really good thing about carbon, it will remove organics, but when you do remove those organics, you are removing them in competition with the PFAS speciation. So you might, if you have a high organic load, you may want to treat that separately because you're going to potentially allow some of the PFAS to pass through the system. How does it work? It is adsorbed into the pore structure, and it allows that material to remain internal to the carbon. However, under certain conditions, pH changes particularly, and preferences for different species, larger molecules being more preferential than very small chains, you can get this desorption back into the stream, and it appears then that your carbon is not doing the job. Dissolved organic carbon needs to be dealt with because it completely competes with PFAS on the uptake. We talked a little bit about the preferences long chain molecules because of the way those long branched chain molecules sit in the carbon. They get hung up faster and better than the short chain species. Branch chains obviously get hung up a lot quicker. We all know that there is a hydrophilic and a hydrophobic end to the PFAS molecules. Carbon really likes that hydrophobic end. The streams that have a lot of different things in them, high TSS, high pH, metals, other things. These multifaceted streams can be problematic for carbon alone systems. So again, we have to look at some of the pre-treatments that may be necessary if we're just looking at carbon as our treatment system. We talked about it removes it very quickly, going back to that 10-minute empty bed contact time. The capacity is limited to reactive sites on the molecule, so you have that adsorption into the pore structure, that reactive site scenario. So we look at the bed volumes, the number of times you can turn that bed volume over. Effectively for carbon alone systems, it's around 30,000 bed volumes. Keep that number in your heads because we're going to see how that competes with organoclays and ion exchange resins as we go forward. So that's the discussion on carbon. What does a carbon system look like? We certainly want to have a robust filtration system up front. Anything that we can do to protect the carbon in advance is going to be an advantage. When you're using a media, I like to go with an upflow reaction. It allows me to utilize gravity as my friend, where as I'm filling up the water from the bottom, gravity will have a tendency to prevent the water from flowing faster in the center or faster along the sides. So you get a much more even flow. And this allows you to have a little bit more contact availability with the media. Now, some medias do work better down to up. But when we're looking at medias for PFAS, the preference from my end is an upflow reactor. So we're going to go from the bottom of the reactor 1 lead vessel to the top, out the top, down to the bottom of the reactor 2 lag vessel, and then out the door. So that's a typical carbon-only system. Let's look at an organoclay. Organoclays are essentially naturally occurring mined material, and they are typically of the bentonite or zeolite sources. So they're material that can be renewed. They're easy to find. There's lots and lots of bentonite and zeolite out there, and there's lots of different forms of the material. Nice thing about clays, they can be blended. They can be blended together as different types of bentonite, different types of zeolite. It can also be blended with carbon. I don't recommend blending them with resin systems because their actionable activities are slightly different, and there may be some problems in the clay coating the surface of a resin, making that surface unavailable. Nice thing about clays is it has a very wide range of specificity. So it takes out the full alphabet of different forms of the PFAS material. This focuses on those long chains and short chains. It's not so great in that mid chain. Does a good job on the branch chain, but it likes the long linear and the short chains most effectively. Very high working capacity. There's a lot of space in clay because unlike carbon, where you're dealing with pores and pore structure, with clay, you're dealing with sheets. And essentially, clay is built up as one small sheet on top of another, and the space in between is where the pore structure is. So there's a lot of opportunity for PFAS to get adsorbed into that space. But there's another piece about clay. It also acts as an ion exchange resin. So you're getting a dual mechanism of adsorption and ion exchange in the organoclays, which again allows for increased capacity. Some of the problems with clays, naturally occurring clays, are very hydrophilic. So the clay is going to require a modification. And in most cases, that modification is the addition of a surfactant. And because of perhaps overzealous production, you might get some excess surfactant in there. So with a clay system, you frequently want to wash it first. Now, manufacturers are now supplying pre-washed clays, so you don't have to do that anymore. So depending on your manufacturing source, you may or may not have to do a quick pre-wash to wash off that extra surfactant. And again, pre-filtration, much like with carbon, is definitely going to be necessary because clay is a much stronger filtering system than even carbon was. So we want to protect that clay as much as possible. So digging a little deeper, you can use organoclays alone. It's again predicated upon the flow, the design, the type of system, what the water is going to be used for. But in a lot of cases, you would have clay in front of the carbon system, and that clay could be a combination of different material clays, and then followed by that carbon system. This gives you a nice dual step removal system. The advantage you have with organoclays, you can get those oils out of there. So this is a really good thing in the area of landfills where you may have some PCBs or other oils in those landfills. You can add some modifications of that clay surface to pull out some additional organics. And we talked about earlier, we want to get those organics out before it gets to the clay. So you might want to use organics, you want to get them out before it goes to the carbon. So you might want to use the clay as a methodology to remove organics if you have a high organic load. There are clays that are being developed now that can remove some heavy metals. So if you've got heavy metals in your water, we can take a look at different types of clays that could help in that area. And the design of the clay is such that because of the dual mechanism, it has a much higher capacity before exhaustion. So you are getting a little bit more bang for your buck. Much faster kinetics. We're down from 10 minutes empty bed contact time to 5. All of this leads to a life cycle where we're improving, not quite doubling, but we're improving our exhaustion curve, where now we're looking at greater than 50,000 bed volumes, whereas in a carbon-only system, we were looking at that, 30, 35,000 bed volume performance. So what does that look like? Again, a strong filtration system followed by the organoclay. And what I'm not saying here is that your vessels are necessarily smaller. What I wanted to point out is the organoclay specific gravity is about double that of clay. So you're using less volume in the same size vessel. So you're able to use the clay in front of the carbon vessels, again, in a lead lag scenario, pull out a couple of extra things, pull out some different PFASs, and then use that use that carbon as your polishing step within the system. Again, you'll notice it's an upflow reaction. We like to keep that through. So filtration, clay, carbon, a complete system. Let's look a little bit at the newer boy on the block, and that's the ion exchange resins. We talked that these are man-made resins. They're specifically fine-tuned for PFAS removal. They work as an ion exchange positively site charged scenario. So they're having an ionic adsorption to the material itself. And these are spherical. Many times they're made of a polystyrene type of a material. And this is really cool because you not only get surface attachment, but you also get internal attachment where the PFAS will actually enter the sphere of the polystyrene and become entrapped within that sphere. So a lot of method in this mechanism is taking place. A lot of manufacturers have different varieties of resins, all of which have a different uptake capacity. So again, you want to know that speciation before you choose your resin, because different resins will have a different desire for a specific species. Really good at removing PFAS to very, very low levels. And most of the manufacturers will always design something that gets you to these quote unquote non-detect levels. Just remember that's still around 2 ppt. Resins last a lot longer, have much, much higher capacity, so you're going to get much less resin media change out. So there's an advantage. They may cost a few dollars more at the beginning, but they have a longer life cycle, so you don't get the number of change outs. So again, you have to look at the total cost of ownership when you're making your decision on what method you're going to use for treatment. Some of the negatives: if you have a high inorganic load, you're going to negatively affect performance. So that means you're going to have some kind of pre-treatment if your inorganics are high. Under the current COVID crisis that we have now, there is somewhat limited availability. Most, if not all, of these materials are made overseas, a lot of them in Asia and China specifically. We're seeing some reduction in production in those countries. We're also seeing some negative import tax that's impacting the price, particularly of materials coming in from China. So we have to make sure that when we're planning, we want to know way in advance the type of material that we're going to be putting into those vessels so that we can secure the necessary volumes. Some of the contaminants, SO4, NO3, some of these other contaminants will negatively impact the resin's capacity to pull out PFAS, because they will also pull out these materials as well. So knowing the composition of that water beforehand helps us to determine what that pre-treatment is going to be. And much like any other resin or any other media, TSS and organic matter needs to be dealt with in advance, because it is an excellent filtration system. If you cover the material with organic matter or TSS, you're going to reduce the capacity of that material to perform. A little bit deeper, filtration is recommended. We just mentioned that. Speciation is extremely important. It helps us to design the specific resin that's involved. If you have a PFOS, you're going to find that resin is going to be a much better application than a carbon or clay design. So again, knowing what you have helps us with that. It really likes the longer chain species. It will pull out an amount of the short chain. It pulls out a reasonably strong amount of the medium chain, but it really goes after the long chain materials. So it's helpful to know what you have. You have the dual mechanism of ion exchange and adsorption. So it has a much higher capacity. And because it has a higher capacity, your kinetics now are very, very fast. You're now looking at 2.5 minute empty bed contact time versus the 10 minutes that we had for carbon. And all of these things add up that you may get that resin to last 1 to 3 years before the need for changing it out. Now, the empty bed contact time we talked about, not empty bed contact, sorry, the bed volume life cycle we talked about with the previous medias were 30 and 50,000 bed volumes. Here we're looking at 100,000 plus bed volumes, and there is some literature that indicates this material might go 700,000 bed volumes before it's required to change out. So that's something to look at. I want to speak a little bit here about regeneratable ion exchange resins. It can be done. However, to regenerate these resins requires a methanol treatment system. And if you're familiar with a methanol treatment system, you have to worry about explosion proofing everything, fireproofing everything. Storage needs to be done for the methanol. All of these things kind of add up to the scenario that if you can avoid on-site regeneration, do it. The savings that you get from regenerating on-site is quickly eaten up by the preparation, the storage, the design of the regeneration system. But there are regeneratable resins that are available. I just prefer not to look at them in the typical type of a system. So what's our ion exchange resin system look like? Again, a good filtration pod up front. Now we're going to have the carbon as your primary treatment system, and the resin is going to be our polishing system. So you will still have a lead lag in the carbon. You're always going to watch that lead carbon vessel. And that's where you're going to be doing most of your change outs. In any of your change out scenarios, when the lead vessel requires change out, you should plumb your design such that the lag vessel can now become your lead vessel. When you change out the lead vessel, that lead becomes your lag. So you're only changing out one vessel at a time. This allows you to get the best bang for your buck in using the capacity of your media to the greatest depth that you can. So that's why we always look at multi-steps in those medias. So those are the technologies that are currently available in the field, readily to install in most applications. The things that are coming down the pipe at this point in time, they're looking at some nanofiltration. And if you're familiar with nanofiltration, these are very, very small molecular sieve type of filtration system, but they are used as a polishing step past media. And a lot of times you see these nanofiltration systems in that under the sink kind of treatment system that you might have in your home. These cartridge-based systems where you have a carbon, a filter, and then a nanofiltration system. You can look at these as final polishing steps in a drinking water treatment system, but they are expensive. There's a lot of work in maintenance of them, but they do have a place in the PFAS marketplace. If we look at electrocoagulation, this is a methodology of subjecting the material to an electric charge, which basically breaks the fluorine bond and reduces the material now into smaller molecular chains. And these smaller molecular chains may be more available to biological degradation. The problem is that fluorine, that free fluorine molecule now, is now in the environment. And there's a lot of literature saying that this is a bad thing. There's some literature that says this is a neutral thing. The courts, shall we say, are out at this point in time on the benefits of using the electrocoagulation as your primary methodology. Again, if you're trying to get down to those extremely low systems or extremely low values of PFAS, you may add an EC system at the very end of your treatment train. A lot of research is being done now on chemical cleavage of the fluorine bond. There's some work in several universities that have developed some materials that will cleave that fluorine bond. Again, some of the same potential problems exist. There's not enough experience in the literature to determine what is happening with those fluorine bonds. But these are things that are being researched, and I personally think that over the next couple of years, we'll see a little bit more of the EC and the chemical destruction of the fluorine bonds coming into play. RO membranes, really good in drinking water applications. There's high and low pressure systems. The only negative is they're expensive, they're hard to operate, they take up a lot of space, and you are now dealing with the concentrated reject water at the end of the RO membrane that still needs to be disposed of in some fashion. Typically, that's done through wet incineration, which can be costly. A lot of new research is going on in the biological treatment area. Part of the problem is PFAS molecules are man-made, not naturally occurring substances. So the magic bug, shall we say, has not been found yet that likes to break this material down. So we're still looking at how to break down this material biologically. That fluorine bond is very, very strong, and it is not a desirable material for destruction biologically. So we're still working, seeing a lot of research in the biological treatment. There's probably a year out before really good, effective biological treatment will be available. So what do? We talked about a lot of information. There's a lot of choices. There's a lot of doors. There's a lot of things that we have to think about before we make the decision. So what do? Understand the chemistry. First step, very important. Define the specific outcomes. What are you trying to develop? Where is that water going? And then after those pieces are well known and well discussed, then you design the treatment system to meet those specific needs. So at Clear Creek and Yukon Technology, we want to be your partners in PFAS remediation by working with you in developing the chemistry understanding, looking at the project outcome, and then not just pulling something off the shelf, but designing a specific treatment system for those needs. So how do we do that? We do customized, fabricate, we self-contained systems. So you can have systems in a Connex box. You can have permanent systems, temporary systems, and they're sized to meet the flow of what your criteria are. So we've done systems where we come out for a couple of 3 days to an airport and we treat water that's been in tanks for weeks or months, bring in a temporary system, treat that water, and bring the system home again. We can do compatible systems with Connex boxes that are self-contained and self-operating, anywhere from 3 gallons a minute to 100 gallons a minute. So again, we want to discuss the type of application that you want to look at. We also have the capacity to do all of the installation, the operation, the maintenance, and upgradability, optimization, working with you, not just as a, here's your system. We work with you to make that system continuously perform. The other thing is, you look at us as we can provide systems for sale or rental. And all of the attributes of a sale or rental system, again, are available through our organization. So that's the discussion dealing with an overview of the technology. And Mike, if you would like to forward any questions that might have come